Hello everyone and welcome to this video looking at some more of the Maths AA course, but this time looking at questions at the higher level. Now there's lots of crossover between the HL and SL courses, but my intention here is mostly to look at HL exclusive topics. So this first one is all about proof by induction. It's a technique that you need to know for HL. You can see here this is taken from section 1.15 of the syllabus. And this concerns proofs. You need to know induction, contradiction, and disproof by counterexample. We're just looking at that first section here today, proof by induction, and this 7-mark exam question asks us to use mathematical induction to prove that the nth derivative of that is equal to this term here. Now, as usual, we're restricted to positive integers for n, and p is a rational number. It's not that tricky, this proof, but it is proof by induction. You have to get all your steps really carefully laid out, so I've given this one 3 out of 5 stars. Let's get stuck in and see how we go. So with all proof by induction, there really are 4 stages to it. You need to begin by stating the problem as a proposition. Now this sort of shorthand, this language allows you to just be really clear about what you are proving. Remember, you're writing a proof here, not just manipulating the algebra. Lots of students get the algebraic manipulation right, but don't really write out the steps of the proof carefully. So step 1, state the problem as a proposition, Pn. Next, we're going to prove the base case. This is normally when n is 1, sometimes when n is 0, but ordinarily when n is 1. Then we have to assume that the proposition is true when n is k. And we need to use that fact to show that the proposition is true when n is k plus 1. Now you've got to be really careful here. You don't just directly prove the proposition is true when n is k plus 1. You have to actually use this proposition to prove that one. And that's really key. A lot of students get this part wrong. They look for direct proof of this statement. You have to show the implication, because that's the inductive step. That's how proof by induction works. So let's have a look at this particular problem then. First off, you can see here is our statement. I've just taken this out of the question, and we write this as a proposition. So we can say let Pn be, I've not left myself enough room here. Okay, let's start again. So we write this as a proposition. We can say let Pn be this statement, and that is that is true when we substitute n in. Now we begin by proving P1 is true. Remember, this is the base case, and this should almost be trivial to prove. It should be fairly straightforward. So in this case, what I'm going to do is I'm going to work with the left hand side and show that it becomes the right hand side. So the left hand side is, remember n is 1 here, so I just have d by dx. That's just the first derivative of x e to the px, and I'd like to try and evaluate that. So this is a straightforward differentiation. We're going to use the product rule here, and I can say that this is going to be, well, I'll begin by writing down x and differentiating e to the px, which just becomes p e to the px. Remembering your chain rule in there, the e differentiates to itself, but because I have a function of x as the power, that's p times x, I need to multiply by the derivative of that to get this p here. And then I'm going to do it the other way around, which is write down the second term and differentiate the first. So x just differentiates to 1, and I have e to the px. So a fairly straightforward product rule there, and now we can just factorize out e to the px, and we're going to end up with px plus 1 e to the px. Now if we go back and compare this to the right hand side of our original equation, it looks very, very similar. The only different piece is that first term where we've got p to the n minus 1. Now of course, if n is 1, that becomes p to the 0. Now There's a few ways you can sort of make this clear. You can, if you like, you can write this out as p1 minus 1 times px plus 1 e to the px, just to be really, you know, heavy-handed about the fact that this is equal. But you just need some sort of statement like, you know, it equals right-hand side, therefore p1 is true. Remember, you have to have those 4 steps explicitly done, so it's not just enough to show this equality, but you need to state it. So equals right hand side, therefore p1 is true. So that's the beginnings of our proof. We've shown that this proposition is true when n is 1. Now we need to carry on by remember assuming that pk is true and using that to imply pk plus 1. So we really need pk to imply pk plus 1. That's different to just saying pk plus 1 is true. We have to actually show the implication. So remembering this is our statement or our proposition Pn. Now I can begin by assuming pk. I'm going to try and write small here so I can get sort of 2 columns of work so we can see what's going on. So we assume pk, that is that the kth derivative of this thing here, x e to the px. Now remember, you've got to make sure you're replacing any n you see with k, is p to the k minus 1 px plus k e to the px. Now that's the step, or that's the proposition I'm assuming. The kth derivative of the left hand side is equal to that thing on the right. Now in order for the next step to be an implication, I have to make sure that I use that result when evaluating pk plus 1. So that's my next move, it's to evaluate pk plus 1. Now, because we're doing proof here, you want to be careful about working with both sides at once. So what I'm going to do is I'm going to work with just the left hand side and show that it turns into the right hand side. So the left hand side here is going to be the k plus 1th derivative. So that's just differentiating one more time than the kth derivative of, again, x e to the px. Now, excuse me, as I said, we want to use the previous result. So rather than try and do the k plus 1th derivative of that thing, what I'm going to acknowledge is that this is a differentiate one more time of the above. And so, you know, a little arrow doesn't go amiss here, just showing that what we're going to put in. Or perhaps we could write it as the left hand side of pk. So dk dx to the k x e to the px, like so. So what we're saying here is we're thinking about the k plus 1th derivative as differentiate one more time of the kth derivative. Now, I know that the kth derivative by above can be written like, so again we leave that dx. The kth derivative can be written in this form, px plus k e to the px, and you can say by pk here. Now, all these little steps perhaps aren't necessary, but we're trying to communicate to the examiner here that we really do know what we're doing. So we're going to be heavy-handed about the fact that we're using the kth proposition. So by pk we have this, and so what I'm going to need to do now is differentiate this thing here using, well, differentiation. Now here's a nice thing when you can look back to the previous part of the question, and often the way that you evaluated P1 will give you a hint for how you proceed here. I've had to use differentiation here according to the product rule, so I think I'm going to try and use the product rule here. So to differentiate this, we're just going to use the product rule. Often you're just going to sort of get used to this and do it in your head. But let's try and be a little bit more explicit, calling these u and v. And so I've still got my p to the k minus 1 out here, and I'm going to have multiplied by u dv by dx plus v du by dx. Remember, with the product rule, because we're adding, the order doesn't matter, and you can call either one uv. But here we go, let's pop this in. We've got k minus 1 here. and I'm going to have px plus k multiplied by the derivative of v. That's just p times e to the px. Remember, the chain rule's nestled in there. E differentiates to itself, but I have to multiply by the p, the derivative of px. And then I'm going to write down this e to the px. I'm just going to leave it at the end because I know what's coming. And du by dx is just going to be p here. And so that's our term. Now we're starting to look quite good. We're trying to think here, what do we want this to look like? We try and think this right-hand side, except n is replaced by k plus 1. So I can see that the power here is going to need to be k plus 1 minus 1. So I need p to the k, but at the moment I've got k minus 1. These are the sorts of things you want to start considering. I can see, however, though, that I can factorize a p out of both sides here. So let's go ahead and do that. We get p to the k, and then we can also factorize this middle term according to e to the px. And so this part of this, the p, remember, was factorized out already. So we're just left with px plus k. This p has also been factorized out, leaving me with plus 1. So it looks like I've got px plus k plus 1. Which I think is exactly what we need, right? Remember, we want our right hand side to be n is replaced by k plus 1. So how do we finish off the proof here? That's looking like what it should be. Now it might be at this point handy to write out exactly what p k plus 1 is. I perhaps should have done this before going through the previous process, but let's have a look. P k plus 1 here is going to be the statement that the k plus 1th derivative with respect to x of x e to the px is p. Now remember, if n is k plus 1, we've got k plus 1 minus 1, so p to the k, px plus k plus 1 e to the px. Now, for finishing off here, since we showed LHS equals RHS, PK implies PK plus 1. Remember, that's the inductive step. Not good enough to just show that the proposition is true. You have to have directly used PK, which we did, of course, here, and we were very heavy-handed about how we did that by PK. We've manipulated everything so it looks exactly like the right-hand side we expected here for the PK plus 1. And we can now finish off by saying since P1 is true and PK implies PK plus 1, Pn is true for all n, the upside down capital A there just reads as for all, by the principle of mathematical, excuse the handwriting, induction. And there we go. Now, marks are quite often awarded quite heavily for proof by induction questions because you have to remember, again, you're not just doing the algebra, you've got to write a full proof. So this last sort of sentence bit here, that often carries a mark with it, and all the other different little algebra steps will be marked in. I hope that made some sense. Let me know in the comments, and thanks for watching.